A tether ball of mass m is attached to a vertical pole by a rope of length L. Determine the angle the rope makes with the pole as an implicit function of the speed of the ball, m, L, and g. So the tether ball is attached to the pole and it's moving in a circle like this. So in towards the center of the circle is going to be this way. So that's different from the previous problem in which we were looking at the pendulum. The pendulum was moving in a circle in the vertical plane, and the tether ball is moving in the horizontal plane. Okay, so we're looking for the angle, and I know if I sum up the forces acting in towards the center of the circle, which is pointed this way, this is equal to mv squared over r. I have the tension, which is acting along the rope, and I have mg, which is acting downwards. There is no component of the force of gravity which is acting in the radial direction. I do have to break the force of tension down into components. Probably it would help to draw another picture here. So this distance here is the length of the string, and this is the angle that the rope makes with the pole. That's theta, which means this angle is also theta. So if I break this force down into components, this is t cosine theta, and going this way we have t sine theta. So if I sum up the forces acting in towards the center of the circle, that is t sine theta, which is equal to mv squared over r. Now I need to figure out what t is equal to. So if I look in the y direction here, I can use Newton's second law. We do not have any acceleration in the y direction, so the ball's not moving in the y direction. I know just because it's going in a circle, it has to have acceleration in towards the center of the circle, but that's in this direction. So the sum of the forces in the y direction is equal to 0. Therefore, t cosine theta is equal to mg. Therefore, t is equal to mg divided by cosine theta. I can take this and put it in for t up here. So putting those two equations together, I have mg over cosine theta times sine theta is equal to mv squared over r. Can cancel out an m on both sides. I can call sine theta over cosine theta tangent theta, and I'm going to rewrite this as tangent theta is equal to v squared over r times g. But I'm not done yet, because this is a function of the radius, but I wasn't given the radius, I was given L. But I know there's a relationship between the two. So the radius of the circle, that would be here, and this makes a triangle. So r is equal to L times sine theta. So I can take that and put it in here. So I have tangent theta is equal to v squared over L sine theta times g. I want to know what the angle is, so I'm going to bring the sine theta over to this side. So I have sine theta tangent theta is equal to v squared times g divided by L. This is an implicit function because I cannot solve this and get theta all by itself. I just have to leave the equation the way it is here. Okay, if you try and do problem 80 with the hammer throw, in the hammer throw, the wire is the steel ball at the end of the wire is swung in an approximately circular path around the thrower's head. This is a path like this. This is not like the pendulum. This path is in the horizontal plane. So it looks similar to what we have here. So if you're doing this symbolically, you have sine theta tangent theta is equal to v squared g over L. And you have a 7.3, well, that doesn't matter, it doesn't appear in your equation at all, a 1.22 meter long wire, so L is equal to 1.22 meters. In an approximately circular path, the ball is traveling at a speed of 7 meters per second, so V is equal to 7 meters per second. So you have your V and you have your L and you have G. You need to find the angle, but you can't solve for theta. So for this problem, you would either have to use a computer or what I would allow you to do for this one is you can use the guess and check method, where you strategically guess what the angle should be and then plug that in to show that the left-hand side of the equation is equal to the right-hand side of the equation. A strategic guess for this problem would be the answer that they give you for theta in the back of the book. So I think in the back of the book they give you 76.8 degrees. So check that sine of 76.8 degrees times tangent of 76.8 degrees is equal to 7 squared times 9.8 divided by 1.22 meters. And if that's true, then that means the angle is 76.8. Well, that is not true, because if I go back here, when I brought the g over to the other side, that was supposed to be in the denominator. So this g should be in the denominator here. And so the 9.8 should be in the denominator here. Okay, so now try. And on the left-hand side, I get 4.15, and on the right-hand side, I get 4.1. Okay, so those are approximately equal to each other. This might actually be closer to 76.7. So they gave me 76.8 in the back of the book. But if I do 76.7 degrees, I get 4.12, which looks good. So that rounds to 4.1. Okay, so we strategically used the guess and check method to figure out that theta is supposed to be 76.7 degrees. Okay, now we're going to go back to problem 89. And if the mass of the ball is twice as large, what happens to theta? Well, the mass did not appear in our equation, so nothing happens. If v is equal to 0, what should theta be equal to? If the speed of the ball is 0, you can try this on your own. You can take a weight and attach it to the end of a string and spin it around. The speed of the object is 0, the object is just going to hang straight down, so theta, measured from the vertical, is equal to 0 degrees. Does your function agree with this observation? Yes, it does. If v is equal to infinity, what should theta be equal to? So again, you can try this out on your own. If you spin the object as fast as you can. Now this is hard to do because usually what happens when you try and spin the object around really fast is it ends up not going in a circle in the horizontal plane. Try and keep it going in the horizontal plane. Spin it as fast as you can. The angle increases. The largest value that you can get for the angle is 90 degrees. If v is equal to, let's do it the other way. If the angle is equal to 90 degrees, sine of 90 is equal to 1, tangent of 90 goes to infinity, so we have infinity is equal to infinity. So yes, that agrees. So if you spin the object as fast as you can get it. So let's draw a picture here. You've got your string like this. You got your object going in a circle. If you spin it really fast, you can get this string to be almost horizontal, but of course you could never get this to happen. So you can't have your object up here and your hand holding the string down there, because there'd be no force if you look in the y direction. Your component of tension would be acting downwards and your force of gravity is also acting downwards, so you couldn't get the sum of the forces in the y direction to work. Okay, so that can't happen. So the faster you spin it, the closer the angle becomes to 90 degrees. Try it for yourself and see what happens.